Wait a minute, why you just do all that?
The original question I asked is answered right here, and then I just asked one more question. I said, what is the magnitude of the acceleration? And to find magnitude, you've got to do a little Pythagorean theorem.
True, okay.
So that is the magnitude of the acceleration of that box.
So the answer on the bottom right corner is the answer to the question that you were asking in the first place, right?
Yeah, the first question I asked
Okay.
for this one was, what is the acceleration?
Okay,
With a vector symbol.
just making sure.
Unlike the previous question where I started out with the magnitude of the acceleration.
Okay.
And just as a side note, if this were physics 151, 131, 151, or 251, you would then, I'd probably ask you to find that angle too. For those who've had trig, this would involve arctan or arcsine or arccosine. For those who haven't had trig, you don't need to worry about it.
Well, sister, Miss, you stressing me out.
Little side note,
Oh, no.
Alright, so let's make the combination of what we did in the chapter, and what we did here with what we did in the previous chapter, a little bit more explicit. A box, a 5 kilogram box, has a steady Newton force applied to it. The box starts at rest. How far will it go? In 5, 7, 6 seconds. All right, so first off, I'm gonna draw the picture just so that I have some physical image in mind here. So, box. Write in 5 kilograms, because that is actually, what is 5 kilograms? Since it's a 5 kilogram box, what is 5 kilograms then?
5 newtons?
No. Looking for what quantity is it? I don't know if you said it over there.
5,000 grams?
I missed the first part.
I don't know if it's right, it's probably wrong.
It's okay, try it anyway.
Isn't it like 1,000 grams, 1 kilogram or
Oh,
something?
yeah, 1 kilogram is 1,000 grams. That would be 5,000 grams, but I'm asking for what quantity is this?
Is this a mass? A mass?
Yes, it is. It's the mass. It is not the weight. Yeah, there have been way too many past tests where I do something like that, and then I say, what's the mass of the object? What's the weight of the object? Weight will never be in kilograms, not in physics.
Could it be in pounds?
Weight could be Newton's most likely. There's some people, when I ask, there's a question that I've done in the past where what's the weight of, I think Nelly or something like that. And a number of people put the answer in pounds. They convert it to pounds as opposed to just multiplying the mass times the acceleration with gravity and just leaving it in newtons. Nothing wrong with newtons for a unit of weight.
Is it, how far we go, is that inches? How far are we going, inches?
In 6 seconds.
Oh.
That's the word in.
Same thing.
All right, So I'm a 7 Newton force. Now I can pick any direction for the 7 Newton force. Just have it. I'm gonna go to the right. 7 Newtons. I'm gonna go ahead and make that the positive direction. Just to make life simple. All right, so it starts at rest. So what does that tell us? What is?
The velocity.
Okay. Initial velocity is 0 meters per second. I know the time is 6 seconds, and if I left the first part out of it, it's not a solvable problem, but the first part gives us key so we can find acceleration. What is the acceleration?
That's the F equals ma equation,
Yep.
right?
That's the one.
.4 meters per second squared.
1.4 meters per second squared. So the problem now is reverted into what we did earlier today. I have an object starting at rest. It accelerates at 1.4 meters per second squared for 6 seconds. It's starting at rest. I can use one of those Hewitt equations. If you happen to remember it, there are other ways, and we'll do it another way in just a moment. So 1/2 AT squared because of this. Starts at rest, we can use this. So that's 1/2 times 1.4 times 6 squared. I know there's a 2 there. That should be a 0.2. The rest of it. 50 something? Oh wait, no, I forgot to divide by 2. So,
I think it's 25.2.
okay. Units?
Meters.
Yep.
And you're multiplying, like, 1/2 times 1.4 times 6 squared?
Yes. Only the 6 is squared.
Yeah,
Some students like to square the whole thing, though. Only the 6 is squared. So it's 1/2 times 0.4, take 2, 1/2 times 1.4 times 36.
smart.
Right. Let's do it slightly differently. How fast is it going after 6 seconds? If it's accelerating at 1.4 meters per second squared for 6 seconds, how fast will it be going at the end of that? I think that was the first example we did.
So will we be multiplying like 1.4 and 25.2?
No,
Is that cool?
we're multiplying something.
Are we multiplying the 1.4 with something else?
Yes.
6.
1.4 meters per second squared times 6 seconds. Because every second, my velocity changes 1.4 meters per second. And we do that for 6 seconds. So we start at 0, then we add 1.4, we add 1.4, we add 1.4 6 times, because there's 6 seconds. So 1.4 times 6,
8.4. Meters per second.
all right. So if I start at 0 and end up at 8.4 meters per second, what's my average velocity?
Is it 4.2 meters per second?
It is. Average velocity is the average of the first and the last one, so 4.2 meters per second. So we could have looked at the problem this way, and then it said, well, if we're going on average 4.2 meters per second for 6 seconds, how far do we go? Well, now you multiply 4.2 times 6, and you get 25.2 meters. All right, questions here?
Yes, how did you get the average velocity of 4.25?
When we're still doing officially chapter 3, we eventually came to the realization that if acceleration is constant, then the average velocity is just the average of the initial and final.
Okay.
Just take the first and the last one and average them together. So take the 0 and 8.4, add them together, divide by 2.
Well, how did I comprehend that?
What was?
I was talking to myself.
Okay.
Wow. Okay.
Other questions? So I want to talk a little bit about why objects will accelerate at the same rate. If I take two objects of different masses and I drop them, that they fall at the same rate. Now, I mean, assuming that the ink inside these things has not much bearing on it, and I'm ignoring the tape too. Will you accept that the mass of this is twice the mass of this?
Yes.
All right, one person will accept it. Thank you. So, if I drop it, you can also think about this as being just two markers both being pulled down. So just because I have two that happen to be stuck together, having them stick together doesn't magically suddenly increase the force that's pulling down on it. It's just the force acting on two markers. So the force acting on this is twice the force acting on this. So this weighs twice as much as that. That's another way of saying the exact same thing. So if I go to the two marker system, and I'm going to make up a number here, this is clearly not the mass of these objects, but I'm going to assume each marker has a mass of 1 kilogram. It's absurdly high, but I'm just going to go with it anyway. So the mass is 2 kilograms. The one marker, the mass is 1 kilogram. The weight of an object is equal to the mass times acceleration due to gravity. Now, we can do this anywhere that we want. No, we'll stick with Earth. So, the weight of this object right here is 2 times 9.8, or 19.6 newtons. The weight of the one marker would be 9.8 newtons. And if we plug into F equals ma, this marker gets sadder and sadder as we go. Well, that means the acceleration is equal to the force divided by the mass. Well, the force, when I let go, is the weight of the object. So over here, the acceleration of this object is 19.6 newtons divided by the mass of 2 kilograms. The acceleration of this one is 9.8 newtons divided by its mass of 1 kilogram. and it comes out to be the same. 9.8 newtons per kilogram for the fans of that, or meters per second squared for the traditionalists. So, because you have a heavier object, there is more weight to it, there's more of a gravitational pull, but there's also more mass to move, and it just balances out perfectly. And now I'm gonna look to see if there's anything I forgot from chapter 4. Because a lot of the stuff in chapter 4 we've dealt with before. Oh, I do remember one thing that. Oh, does he do friction in the chapter 5? Yep, chapter. All right, so I need to talk about friction. Any questions before we talk about friction? So let's start out with what causes friction. Well, let's identify some stuff. I have a book here on a table. I push it. Now Newton's first law says that that will keep on going unless there's some net outside force causing it to stop. That objects need to be forced to stop doing whatever they're doing. Right now, it will stay stopped unless there's some outside force that causes it to start moving again. All right, but as I move it, will you accept the fact that there's something slowing it down?
Yes.
All right, it looks like we got 3 people that time. All right, we're moving up. Now, it was sliding against the table, there was some rubbing going on there was friction. What do you think affected the amount of friction acting on the book?
The amount of force applied.
That I pushed on it? And we'll take a look at several of these things. So I'm writing down what people say, and then we'll discuss whether science agrees with you or not. Applied force. See if I can write that slightly more neatly. I think slightly works there. Any other speculation?
The surface area of what's touching.
Surface area of contact,
Yeah, that's a better word.
or contact surface. Hopefully you know. You know what I mean.
Is applied force the same as, outside forces?
I think what Becca was referring to was the force with which I pushed it.
Okay.
The weight of the book.
Mass of,
Yeah, I don't know whether it's weight or mass.
And
I was gonna say the mass of the book,
any other speculation?
Gravity? Or would that just be the weight?
I would lump it into weight, depends on which aspect of gravity you're talking about, but,
I think it's the.
okay, we'll keep it with weight. All right, we'll start with these. All right, so the applied force, was the friction in what way? That, because I only touch it for a very short amount of time, so what effect are you picturing that the applied force has on the friction?
So if you pushed it with like a force of 5 newtons, the friction would act up with another 5 newtons to make it slow back down.
So friction remembers what I did? So you're saying that once it's no longer touching me, that the 5 newtons is still applied or not applied?
Not applied.
Okay, so the 5 newtons only while I'm touching it.
No, I think it would still be applied.
So it remembers what I did.
I guess not.
It's gonna track me down in the middle of the night. Yeah, there are no Jedi powers involved here. I can't influence him from a distance in that way. So, yeah, the amount that I'm pushing with it, yeah, so,
And that's
Backing
what
up
I
just a
was
second.
talking about when I was saying outside forces moving it. There's no more outside forces to either continuously have it moving or stopping, because that's a book that does not have no type of nothing unless someone's moving it.
well, let's be careful. There's still, it does stop. After I stop touching it, the book does stop. So there's gotta be something stopping it. So there is some outside force. From the book's point of view, there's some external force causing it to stop. But it's not me. I'm not causing it to stop because I don't have Jedi powers. Or I deny it. Neither confirm nor deny.
Yeah, I was mixing it up with the box examples, but like they have a constant force, so scratch what I said.
Yeah, so the amount of force that's being applied does not, there are certain situations where you can indirectly apply it, but not in this particular case. So the applied force, basically motion doesn't have any memory. It has no idea what happened. It's like a goldfish. It has no memory of what just happened. So applied force actually does not have an effect other than the applied force got it to move to begin with. If there's no applied force, if I don't touch it and the table is perfectly level, there's no friction acting on it right now. So my touching it caused it to slide, or gave it its desire to slide. Surface area. It's a little bit tougher one to test, but we do have the friction boxes somewhere in there. And is that gonna fall out? Yes, it will. Trying to give it enough heft so that we actually get a decent reading here. Alright, will you agree that that is a different surface area than that is?